listening today. We're going to start in about like 2 minutes. So this is Grace Tan-Wang, and she is a Principal Systems Engineer at JPL. Today she'll be talking about a little bit about her job as an engineer and about some projects that she's been working on, such as the Europa lander. So I hope you guys all enjoyed listening to our lecture today. And then to you.
Okay.
Thank you.
All right. Hi, everyone. All right, I just want to get a sense of the crowd here. I see that we have a whole spectrum. How many seniors do we have here? All right, be proud. Okay, that's a good representation. Juniors? All right, almost sort of as many. Sophomores? Freshmen? All right, freshmen. I like that. And then everybody else that didn't fit in that category? I want to make sure I hit all your interests, and I applaud. Yeah, the up and coming. Okay, so as Madison said, I'm an engineer at JPL. I've been there. I'm on my 38th year, so I thought I'd title this a little more from a personal perspective. I know you've heard from other JPLers, and so those are great too. But I also wear a few more hats. I work with the Space Academy, which is how I met Madison and some of the other students that were chatting with me. We have a space, and Amy here, who is a co-director with me among other people. We hold a program with the 4 high schools here with JPL and carry out a mission. So I hope those of you that haven't been a part of that will look into it. But this is where we can kind of merge the high school interest. Typically it's sophomores, some juniors and seniors mostly, and we build a mock spacecraft or mock mission, and we challenge the students to form teams, their own project, and accomplish a mission. So that's the other hat, and I want to engage you, and I want to sort of gauge the interest in space for that. And then the other hat I wear is I actually interview high school students for college. My alma mater, MIT, engages the alumni to interview the students, and so I have some perspective, and I've done it for like 20 years, and so just getting a sense for how to bridge from the high school to your future if you're planning on going to college, and hopefully add any insight or answer questions if you have that. So I'm here as a resource, and but as Madison said, I wanted to share some of the exciting projects that I've been working on in my time there. So from my personal experience, I've started at JPL working, well, I've been a systems engineer from the beginning, but I started working on a mission called Cassini, which you might have, some of you hopefully have heard of. It was a mission to orbit about Saturn. We learned so much about the moons and the rings there. I worked on the spacecraft side of it, and on the system side to pull together all the subsystems and figure out what we need the spacecraft to do in order to survive a mission at Saturn. And then I moved into some of the Mars missions. My first one was Spirit and Opportunity. Hopefully some of you have heard about that. It's a solar-powered rover on the bottom there. They were great. We made 2 of them. We landed 2 opposite sides of the planet, and they survived way beyond our initial estimation of their mission, but they were solar powered, and so they were constrained to explore mostly around the equator because that's where we can get the best sun exposure. But then we ventured to want to explore further away from the equator. We made nuclear powered rovers, and I think you've heard about from MSR Al Chen, who I work with. We built Curiosity, which used a different way of landing, very exciting. Al is very close in touch with that design, and we could explore beyond the equator. And Perseverance, the more recent rover, also is nuclear powered, and that's where we're gathering samples and looking to bring another mission there to pick up the samples and bring it back. I don't want to spend too much time about Mars. I know there's a lot of that in the news, and a lot of other JPLers that may have shared that with you, but it is a very rich area at JPL. More recently, I've been involved in technology. So from an engineer's point of view, we want to keep pushing the limits on what we can do. So missions like Cassini and Spirit and Opportunity, Curiosity, Perseverance, these were science-driven missions, right? We're there to enable scientists to be able to gather data. But what about exploration within the technology area? We need to be able to improve our functionality so that we can do more and take the mission. So I was part of a mission to go to Hawaii. So we tested new parachutes, new decelerators, and Mars has an atmosphere. And so how do we increase our capability to land bigger and better things on Mars? And so we did a test out in Hawaii that I hadn't planned to talk about, but I have some backup slides. If that's of interest and we have extra time, I can tell you about that. But I got to spend several months in Hawaii for each of the 2 tests that we had there. And then lastly, and that's where I'd like to share a little bit, I've been spending the last couple of years on a mission to Europa. Europa is the moon of Jupiter. It is one of the highest candidates for where we might possibly be able to find life in our solar system. And so I'll tell you a little bit more about that, but I'm super excited. And the reason why I think it's relevant here is we have started the concepts, we started the technology for it, but really it's the people in this room that will be able to make it happen. This is a future mission launching probably a decade from now. So we need, bright, energetic, forward-thinking people to make this happen. So I challenge you to keep that in your horizon. All right, so let me tell you a little bit about Europa. So our main goals for going to Europa, this mission, is that we want to, and I'm sorry, it's a little hard to read probably, but being the first surface mission, we actually have a couple of missions already targeted for Europa. You may have heard about Clipper. JPL is currently building a mission, a spacecraft, to orbit about Europa and take much more detailed science and data to study here. The last data we had of Europa is from Galileo back in 1990s. And so the information is only as good as that. We need to go back. That's when they found evidence that there was an ocean underneath a relatively thin crust. There's twice as much water on Europa than is on Earth, even though it is, a fraction of the size of Earth. And so it has all the ingredients and the chemical energy to harbor life potentially. And so the goal of going to the surface, but what you need as the next step is to go and touch it, to taste it, to see what's actually there, measure that. And so our challenge for a Europa lander is to look for evidence of biosignature by actually, making the measurements on the surface. We want to assess how habitable it might be, and then do the characterization of that environment, of the surface and the subsurface. Okay, so why is it hard to land on Europa? Well, first of all, the Jupiter environment, you might have heard from the Galileo mission, is highly radioactive. It is many times of what we here experience on Earth. For example, when we go to Earth, we're talking in the single digits of kilorads of exposure. When we go out to deeper space, we go to Mars, we talk about getting up to maybe 50 kilorads. When we're going to Europa, we're talking about megarads, and that's after we put in, thick shielding of our electronics. And so we have a high radiation environment, which means our electronics are just not going to last that long. We also don't know enough about the topography at all scales, right? Are we landing in a Grand Canyon? Are we landing in the flat desert? There is just so much variation and unknowns about the planet. How do we get to the surface in a safe and successful way? And then the temperature at Europa is also extremely cold. And so for us to analyze the sample, we're challenged with not modifying it, but our electronics have to operate in a very warm environment. So how do we extract the sample and analyze it in its most primitive state and get information before it melts and alters? So those are the environmental challenges. So as a result, for the first mission, we're going to manage the lifetime. We're saying that with a high radiation environment, let's just survive to our current capabilities. We're looking at an order of a month or two on the surface, which is much different than what we're used to on Mars, right? Mars, we live for at least 2 Earth years, but often much longer. So we're talking about sort of on the order of a couple months. So we have a primary battery for most efficient mass ratio, so that, you know, if we have to build in a RTG, which is the nuclear powered module, or rechargeable batteries with solar arrays, that's a lot more equipment that we have to bring. So with the primary battery, we have a more efficient mass ratio, but it's a limited life. We also are challenged with how much data we can bring back. As you know, Europa is at least 5 times, depending on where Earth is and where Jupiter is, but it's up to 5 or 7 times further away from where we need to be communicating, and so we're challenged with how much data we can actually bring back. But our main goal to get to on Europa is to grab a sample, taste it, measure it, find out what's there. And so the first goal is to assess our sampling site once we land. How do we get the lander to be able to select a suitable landing sample site? How do we, it's really hard to read, sorry, how do we excavate? So we want to get beyond just the surface, right? We figured that there will be some modification, alterations from the surface, from radiation and other environmental effects. We want to get below to get something a little more primitive, and so we'll excavate. We want to dig at least 10 centimeters deep. And then we want to be able to collect it and analyze it in a timely way, keeping the temperature of the sample cold so that we can get as close to the native measurement that it has. Okay. Oh, I didn't see that, yeah.
What causes Jupiter, or the area around Jupiter, to be so radioactive?
That's a great question. I think it's the way that planet was formed. It created a high radiative, but that's a great question. I don't know why it's high radiated. But that's what caused, that was the biggest challenge for Galileo when it went there, and it's centered around the Jupiter body. So if we can, and that's what Clipper's strategy is. It's a highly elliptical orbit. So if you think of Jupiter with a cloud of highly radioactive, high radiation environment, what it does is it kind of dips in to take the measurements, and then it comes back out. So it's a bit like if you stuck your hand in hot water, right? If you kind of just stuck it in for a second and then stuck it hot, you could do that multiple times rather than just stick your finger in and keep it there for a long time. And that's what the lander, unfortunately, would have to do, right? Because it would land on Europa and just be in the thick of a high radiation environment, and so that's what causes the short life. So the idea is that we want to use, with a short life and limited data that comes down, what do we need to enable this mission? Well, we looked at autonomy as a way to enable this mission, right? So now we'd like a smarter lander, whereas on the left-hand side is our rover. Our science MSL is the Curiosity rover. To give you a sense, right, it survives. It's there for, our nominal mission was 2 Earth years, but it's continuing on. I think it's over 10 years now. We get over a kilobit per second. I know that's kind of a random number, but just to give you a reference, right, a kilobit, so it's 1,000, it's 1,000 kilobits per second, right? So we get 1,000 kilobits per second. It takes us 7 minutes to send the signal back and forth. So, you know, we get a fairly quick response with what we tell the rover to do, and then when the rover has data, to send it back. And then, and we have time, so we have time. We have it took us 180 days before we got our first sample, because we could explore and learn about the rover. We just have the luxury of time. And we talk to it every day. We actually, the cadence with the rover is that we get the data down. What did it do today? It drove towards a rock, and so how do we want to now analyze this rock, how do we want to sample it, what instruments do we want to use. We can plan that each day, and then we send it back up, and then the rover executes its mission. Conversely, so it's a very ground-driven mission, right? Ground is what tells the rover to do what to do every day. We also have the counterpart. You can imagine, gosh, if you had a really short mission, in fact, Cassini carried a probe, the Huygens probe, and that's the picture there, where we pre-canned everything. It was gonna fly through the atmosphere, land, deploy a bunch of instruments, take some data, and send it up. It's all pre-canned, no ground intervention or ground in the loop to tell it what to do. It's whatever we thought we wanted to do, and if it worked, it worked. If it didn't, then that was it. But that's, and that's quite limiting too, because it's only to what we know before we land there, but we can't really teach it what else to do once it gets there. So what we want to do with the lander, with 2 months, we want a chance to be able to say, okay, now we see where we've landed, we've seen where one sample got certain kind of data, how do we proceed with the second or third sample? And so we want autonomy and ground to both work to enable this mission. And so we took the last couple of years and explored autonomy, and we broke that down into certain levels. And so one of the more challenging areas is going to be sample autonomy. The idea that if the lander arrives, we can feed it as much data as we know before getting there. But once it lands, it will have the best information, right? It will take imagery and look at the terrain and understand what it can and cannot do likely. And so we want the lander to adapt and learn on its own. So we have a team. In fact, we've done different levels, and I'm going to show you more ideas of what they explored. We have a sampling autonomy team, and that then is built into the overarching mission autonomy, which is now the whole lander will also figure out, based on what the sampling autonomy did, what instruments do we want to use, what data do we want to send back, and what do we want to do next. So we layered our autonomy in this fashion. And so the elements that are circled in red are what we prototyped these last couple of years. So for the sample autonomy, you'll see in this picture, on the top left image, that's our raw data from Galileo. That is what Europa looks like, and that's the resolution we have. It's about 6 kilometers in resolution. So what the scientists have done is derive what they think that material could be, along with the temperatures and the scales and the hardness and the composition. And we built, to the right of that, samples of Europa. We've actually tried to construct Europa hardware in our labs and kept it to the cryo temperatures in order to see how our tools and instruments might work in that environment. Then we built test beds. It's maybe not as easy to see from a distance, but in the lower left-hand corner here is where we then built in hardware arms with like 5 degrees of freedom and with various different tools to now experiment and use autonomy. We had cameras, perception tools that would take imagery and then exercise the arm and then feed that back. If it took too long, how to readjust and make that objective work. And then we also use simulated environment. The bottom right is where we then also created a simulation of what we thought the European environment would be, and then ran our algorithms and tools within that simulated environment to see how well it would work. And with this, we were able to build up a pretty robust sampling algorithm that could adapt to a certain range of tools, and we could see that work in several trial runs. Then we also built the mission autonomy. So within the sampling autonomy, it is wrapped around by the mission autonomy, which takes what the sampling autonomy does, but then puts it back with the rest of the mission. And so the idea is that the sampling might grab a sample, and now the mission autonomy would figure out what instruments could use that sample, what sort of data was received, if it was a positive or a negative indication of biosignature, and then figure out what data to send back down to Earth. And so we use two prototypes within that we have at JPL. There's the M-Exec planner and executive that can accomplish those objectives, as well as another type of algorithm under the program Trace that also ran. So with two separate approaches to how we could do this auto planning, if you will, take the results, feed that back into the plan, and execute now the new plan. We use both of those to help us demonstrate that we have a way to develop a whole mission level set of algorithms. What the videos are showing is in the simulated environment on the upper right in the white, those boxes that are highlighted, that's the box that's active at the time, right? They kind of go through each step. We're ready to take images. We're ready to decide where to sample, and then let's execute the sampling algorithm, and then they go, and how much power does that take, and how much power do we have left? Now, do we send the data down through our radios, and then do we sleep? Do we get too hot? So there's thermal management, there's power management, there's data management, all that ongoing on the lander, which typically we do from the ground. I mean, I will say that on the rovers, that is all mostly controlled and managed by the ground. We're asking the vehicle now to do it. And then we integrated that together. There were, beyond the autonomy task, we also had a team that looked at how we might land on Europa. We also had teams that were actually building the arms and looking at different types of tools that they might use. We integrated, we wanted to do a system level demonstration. We took the mechanical design of the lander, which actually I should be using my cursor here. So here's the mechanical lander test article. We also took the arm that another sampling team had been building up and prototyping. We overlaid our sample autonomy that the team that I was working on had, as well as the mission autonomy, and collectively pulled those all together in the lab and integrated them so that they could all work together. We had all these different, new technology areas that we're exploring on their own to figure out what worked and what didn't work, and picking the best from each of those, we put it into a system that could be an example of what a future lander might be like. And then we took it out to the Arroyo. Those of you that were part of their Space Academy, it's the same Arroyo that you guys were doing the testing on. We did a Arroyo testing of our system as well, just to see how everything works together and how well it could respond to new environments. And we might set up a new rock formation or new terrain that it didn't expect and see how it would react. And then we wanted to bring it to an even more, Europa-like environment. So we actually took the whole test setup to Alaska, to a glacier. And that was this last summer, late August, where we selected a site that we thought could emulate Europa and watch the system work within an icy, cold terrain. So it was quite successful, and as always, we learn a lot from doing this type of testing. And then beyond this flight system working together, we care about just how do we actually use this in a mission. We call that concept of operations. So the flight system box noted on the top left would be our lander. The data comes down in the downlink, our ground system, and the scientists and the operators, engineers here at JPL typically, they receive the data, and we tell the vehicle what we want it to do next. So that would be sort of the uplink. But when you introduce autonomy into the mix, we can't tell it exactly what to do. Now the lander is thinking for itself what it wants to do next. How does the ground keep in sync with what the vehicle is doing? And so we did some experimentation on how to go about figuring out that architecture. How does the ground now work with the flight if the flight system is off, also making its own plans? And so we used a concept called design sim, which is a mock operations. So we explored a concept of operations by laying out example missions. This is a timeline model. This is actually, this is really impossible to read, but the idea is that this is showing all different types of mission runs that we could imagine. You know, what if we did 5 samples? What if we did 10 samples or 20 samples? How much energy would that take? You know, how much data could we get down in each of these missions? And so we ran all different types of mission concepts, and then we put together some mock operators on the ground. We had real scientists actually, our Project Europa Lander scientists come in and look at this data and tell us what decisions they wanted to make. And we could see how well they could interact with the autonomy and what sort of decisions they would want to make. So all of this, you know, we demonstrated different, at least a concept of how autonomy might work on Europa, what types of hardware, what sort of decisions we want the vehicle to be able to make versus on the ground. And so, you know, the key here is that we're just building the paths to this future mission. Europa presents a lot of exciting and possibilities of worlds that we don't know yet. It could harbor life. We want to go there, but it has a lot of challenges, engineering challenges that we need to overcome. And you know, it's the prototyping that we did here with the autonomy, as well as the other teams that worked on the landing system and the sampling arms, and we had, you know, many others that we did over these last few years that will enable this future mission. And I'm here to get you excited about Europa so that you can be our future engineers on this mission. And I think that's my main few slides on Europa. I also wanted to encourage you, whatever you end up deciding to do, I think it's important to look at what gets you excited, right? There may be reasons why you want to pursue a certain path because, you know, you can make a lot of money, or you think that this is where the world is going today. But in the end, I think going also including with what you're excited about is an important part of your future path. I myself, you know, when I was in high school, I tried to think back. I really enjoyed my math and science classes. My parents were engineers, but I don't know that they really biased me towards engineering necessarily. I think they maybe could help me with my math and science problems a little more than history, but or English. But really, those are the classes that spoke to me. I enjoyed physics. I actually went into college thinking that I would look into mechanical engineering. But when I got there, I found that there were so many different other options. And so at MIT, they had an aero-astro department, which included a lot of the disciplines from mechanical, but really specifically applied to aeronautics and astronautics. And so that sort of resonated with me, and that's where I ended up going with my degree, and it brought me here to JPL. In fact, if you had told me sophomore year that I ended at JPL, I would be like, I don't know, maybe. But you know, you got to take one step at a time, but figuring out what looks like the area that is exciting to you, and I could see myself doing that, or I want to learn. I wake up every day thinking, oh, that would be, you know, exciting to do, and I want to start this task or work with these people. That's, I think, what helps you figure out a successful path. And once you figure that out, I think it's important to do your best, right? Work hard. It's okay to fail. You learn just as much from failing as you do from succeeding, and so it's all part of the learning process. And then it's important to, I know for me, just to work with people and have the support with the people around you. A lot of that positive and support really goes a long way to helping you take that next step. All right. That's all I have. How did I do on time?
We can do a Q&A portion right now. if you
Okay.
like.
Do we have any questions? Yes. Sorry, yes. That's a good, yeah. So it's a multi-pronged approach, right? It's not just a stick a finger in and, or did you find we used to joke, you found a whale, while we're there. So we have multiple things that we're looking for. I think what the science team, and I'm speaking for them, I'm more on the engineering side, but there's sort of a whole bunch, there's the composition, right? What sort of organic or inorganic materials we find there. There's things like abundance of certain elements that they're looking for. So there's instruments that are targeted for that. There's chirality, right? There's a left-handedness or right-handedness of organisms that they look for to see how that is. There's what's some other ones? There's I think just from the imaging they can look at just how the shapes and symmetry and characteristics there are. So we have 5 different instruments right now, targeted or outlined for the Europa lander that are looking for each of these elements. And part of the autonomy that we are looking for the lander to do is that typically all that data just, mountains of bits would need to be sent down, and the scientists could then pour through them and see how they kind of relate to each other and see how that, forms an opinion of whether there's a positive or negative. And so what we're asking for the lander to do in the autonomy sense is try to curate some of that data, if you will, right? Just if we put some thresholds and then sort of relativeness of different thresholds, because sometimes one positive thing here, but we actually gave it a nickname. We called it biosignature bingo, right? The idea that, there's multiple characteristics that we're looking for, but if there's 3 or 4 of them that are more on the positive side, then that might be a good indicator that there's something interesting here, versus one that was kind of positive and all the rest were negative. That may not be as interesting. And so it's a great question. It's a definition that the scientists have done their best to try to define, but in the end there's some amount of data that needs to just come down for the scientists that require the human interpretation to make sure that the right assessment or decision has been made. Yes.
What's the general timeline for the Europa project?
Great question. So right now we are focusing our attention on Clipper, which is launching next year to be the orbiter. I think the idea is that based on that information, it could better guide when this mission could go. So I think it's in the next 10 years, I would guess, right? Clipper is going to arrive at Europa in 2030. So I know, sort of adds up quickly, right? And then so based on that data, you can imagine in the 2030s getting this project going so that we can address the findings.
So that's
of
why you're
Clipper.
saying the people in this room are the people that are going to do it.
Yeah. Yes. Enyo.
Hey, I'm wondering if you could talk about the and then we could talk about the running of the mission, because I know from the facility that was potentially doing the
Yeah. That's a great question. It's actually.
But this mission is intentionally
Yeah, no, it's actually a really good question. You'd think I planted you to say that. So planetary protection is a big deal, right? We're going there to find evidence of life, but we certainly don't want to bring any of our own life there to contaminate or, first we don't want it to contaminate any of our findings, but of course we don't even want to contaminate what's there. So planetary protection is a very big deal. it is addressed at the global level. NASA, with all the other agencies, work to define what is a acceptable level of cleanliness for both forward and backward, which is, you know, what we bring there, and then if we bring any samples back, of course, like sample return is not Europa yet, but if you bring samples back, we don't want to contaminate anything here. So it is very much a big deal. We can never achieve zero, so that would be great if we could somehow guarantee that, but we don't. So it's all you know, per square area, how much contamination there might be. And we do lots of levels of sterilization, heat, chemical, that sort of thing. And then once you sterilize it, how do you keep it clean as we're putting everything together, and if you have to rework it. So it's a very thorough and thought through, right? Once you have something clean, it's locked in, you don't want to have to reopen it, so we have to think about how we do the integration and then measure and guarantee that we have met the required cleanliness. So it is very important. It's dealt with at, you know, the international level. NASA has a special office just on what missions have to do to meet the requirements and accept it. They review what our projects do, and then you know, make sure that they agree with what's been done. Hope that eases any concern that that we might have on planetary protection yet. Anything else?
Is there any project after Europa, any other project that NASA is thinking of beyond Europa, going beyond Jupiter or our solar system?
Yes, Saturn actually is further than Jupiter,
Yeah,
right?
yeah.
And then Voyager, if you've heard of that mission back in the 70s, the Grand Tour, it flew by, you know, Neptune,
And
Uranus,
Pluto,
and
yeah.
now has left our solar system, right? So we do have missions that go, you know, well beyond our solar system even. Are you asking about
Like
orbiting?
landing somewhere, like in one of the.
Yes, so, and we do have more in the works, right? Not necessarily at JPL, but there's studies for a mission to Enceladus, which is a moon of Saturn, and so that also is one of the icy moons. There's a whole family of ocean worlds, if you will, you know, bodies that we think contain water and so are worth exploring for future potential life. And so Enceladus is there, and Titan is another one. And so, yeah, and there's mission to all of those. I'm a little biased towards Europa and working with our scientists. They're like, this is the place to go, but there's definitely more than Europa to explore. And they're all really exciting. There's another mission I haven't personally worked on. I've been on a review board for it called Dragonfly, and that's going to Titan. It's going to land on Titan. It's going to hop around like a grasshopper, and not drive, but fly like a drone.
Oh, okay.
Yeah, and explore that way. Yeah, no, space is really exciting. I encourage you to Google and look at all the various missions. We encourage all the bright minds to come and help us achieve those missions. Any other questions?
Why does Europa look the way it does with all of its?
Yeah, with the cracks. Let me see.
What was the question?
Oh, the question was, why does Europa look the way it does? So, best the scientists can surmise, right? Some of the coloring indicates what sort of materials that be. I think it's got a high salt content, my understanding, and so sodium helps with some of the coloration there, and I think it reflects also some of the modifications that might have gone on with like radiation, might be some of the darker spots, if it's been exposed more to, you know, that environment. The cracks are fissures, the idea that there's some movement in the plates, and so that's where some of the fresher material, and that's helping us decide where it might be more interesting to land, right? Some of the cracks could be more challenging to land because there's been movement there with, across the plates, but also that's where some of the newer material might be, because that's where, jets or other, material from below could end up being pushed up.
So it has plate tectonics going on
Yeah, that's some of the,
with the mass of water.
right, because below is a liquid ocean, so there's some current. There might be thinner areas of the crust, and so that might cause some of the movement. Yeah.
One more of a practical question as an engineer. You've obviously chosen a field where your time horizons are very long, lead measured in years and decades, and the result from conception to either success or failure is very binary, right? If you applied your skills to a different field within engineering, you would have more immediate feedback or more kind of timely feedback. How do you deal with that just as kind of a daily practical matter? Is it psychologically more difficult to be on long lead projects that have a binary outcome like this?
Well, so kind of two responses to that. One is, yes, it's true, right? I typically work on a project like 3 to 5 years. It's typically about a 3.5-year development. Depending on the project, some are more challenging, might take longer. But typically 3.5 years from sort of the green light from NASA. There's a whole sort of what if. So this is still in the conceptual phase. There's a lot of great ideas, let's explore this further, but they don't quite make the cut kind of thing. And so there's a lot of work in that area. But once NASA gives the green light and says, we're committed to give you the funds to get to launch, right? That's about 3.5 years to get to the pad. And so I've worked on several of those projects, right? And so it is a greater timeline than some other lines of work you might imagine. But that gets broken down, right? It's not like, okay, once I sign up, it's sort of an endless turn until we get to the pad. It's broken down to different tasks. Like we have a deliverable to get to a design that's accepted. We have another review for when we build the test. We're ready to start testing, or ready to do, ready for launch. And so the work does get broken up. I'd say we're more, probably more, I don't know, 6 to 12 months is sort of more of the time scale of the major chunks of work that we do, which maybe in your mind that's still long, but it's also the only work I've known. I came straight from undergrad to JPL, and so that's the world I work in. My sister works in the consulting world, and she's like, 3 months we're done, in and out, and so that's a different line of work. And I look at that and I think, how do you make a substantial contribution like that? 3 months is a smaller piece of a bigger task, and I like that 6 to 12 month time frame. Yeah.
What disciplines or majors, single prospective students in the room, what disciplines or majors apply from the students in the room at the state university to contribute to these missions?
I'm not
Sounds
sure.
like coding was a discipline or major that you pick for people to work, potentially work at JPL and contribute to the missions,
Oh, so the question is, what sort of disciplines
or majors.
our majors are used in
Right.
missions and projects? So the answer is a wide range, right? I was aerospace. It kind of points to a lot of more of the space types of work, here in Southern California. But every project has that whole spectrum, right? We need electrical engineers, computer science, mechanical, and both electrical and mechanical, they come in so many different flavors, right? In the electrical side, we need the folks that design our radios, that design our computers, that design our sensor boards, our instruments. In the mechanical, there's thermal engineering, there's propulsion engineering, there's mechanisms, there's the robotics. So it's that whole spectrum, right? And then that's just the engineering side, and software, right, kind of permeates everywhere. But then there's also the science side. We have physicists, geologists, you know, the biologists, the astrophysics, they're all, right, they're all part of this whole little world that we build around each project. And it takes all of that to, you know, to come together so that we are, you know, we have what we have. So, right, yeah, so someone that's a physics major, you might think, oh, well, they might not fit at JPL. It's like, no, absolutely, and what we find is at JPL, for those of you who know, just looking at JPL, but you want to come back to La Cañada, it's a lot of, I would say a large percent of the folks come here because they also love the space exploration of it, right? I mean, I'm going to be honest here, you can make more at some of these other more lucrative tech companies, right? But it's the love of space to know that we're working towards, you know, finding new science and data and answering questions that we don't know the answers to. That's what really pulls the people at JPL, and it makes it. How I ended up there 30 plus years. You could have told me that out of college that I was going to stay here for that long. I would have said, no way. I can't imagine that, but here I am. Yes.
Is autonomy important to this mission because of the short lifespan on the surface?
Yeah.
Are there other projects where autonomy is going to be used in the future?
Great question. You can imagine how once we have, you know, proven and shown this autonomy, it can be used in lots of future missions, right? One of the challenges at JPL is we're trying to do a lot of first of its kind new things, but we try to be, you know, respectful and fit within a certain budget, right? We don't have infinite resources in terms of dollars, and so sometimes it takes a technology that enables a mission, not nice to have. Like if, you know, I think a future orbiter or future, you know, Pluto mission or wherever else we want to go, it would, once it's been proven, I think it becomes less risky and more cost effective to use again in future missions. But it's hard to rationalize it or establish that if it's not necessary, right? Because now it's just added cost. If something was estimated to be this, but oh, if we added autonomy, it could be so much cooler, but it's going to cost incrementally this much more. We can't justify that. But when it enables a mission like this, and that's how we can get to the surface, okay, well, then that's what we have to do in order to explore Europa. But once that's been developed and proven, I think it would benefit many future missions. In fact, I know it would, and I think that's what NASA's looking to do, is by developing that capability, it will feed forward to future missions.
Okay, great. Thank you everyone for coming today.
Thank you.